So this is talking about kind of mathematically how they came to understand the shapes of these orbitals. And we mentioned earlier it's a probability map, sort of. So you can look at the probability density. You end up with an s orbital that is spherical. Is going to be something like this. So notice that this is composed of a bunch of little dots. So you can think of that as being a multiple exposure photograph, right? Where the camera's sitting there and you take a picture, and the electron was there. And a second later you take a picture and the electron's over there. And you do that like a million times, and then you get this shape. And notice it's kind of fuzzy on the edges. It doesn't have a distinct edge, but there's more possibility of the electrons being found in here than out there. The problem with using the probability density is that you end up with the highest probability being at the nucleus, which is one place where the electron cannot be. So they do something different. They use the radial distribution function, and blah, 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 blah. And when you do that, you get something that looks like this, where at the distance from the nucleus, the probability of finding the electron here at 0 is 0. As you move away, the probability of finding the electron gets bigger and bigger until it gets to a maximum, and then it falls off again. So there's this place in the middle of that fuzzy dot picture where the electron could not be found. So calculations with this give us this maximum at 52.9 picometers, which happens to be the same number that Bohr predicted for the radius of his first orbit. So the number's the same, but conceptually there's an important difference. For Bohr, the electron was always at 52.9 nanometers because it was going in a circular orbit. But in quantum mechanics, the electron could be found at multiple or at different radii, but 52.9 is the most probable. So the 1s orbital is spherical. Spherical starts with an S, so that's kind of a nice coincidence. 2s and 3 orbitals, also spherical. Their principal quantum numbers are larger. The orbitals are larger in size, and they're higher in energy. As we get into these higher quantum numbers, we're going to have some nodes in our orbitals. A node is a place where the wave function goes through 0. So in this s orbital, there is a node at the nucleus. The electron cannot be right there. This is an illustration of a standing wave on a string or a piece of rope. If you vibrate the end of the rope just right, you can set up a standing wave. And it blurs, and so it kind of looks like this is a solid thing, but it's not. And then it has this points where the string does not appear to be moving at all. Those are the nodes. So 2s and 3s have a node. So we're just going to ignore those probability densities because that's not right. So for the 2s orbital, it's got a little blip here of probability, and then there's a node, and then the probability goes up and down. And for the third one, there's 2 nodes. So each principal energy level has an s orbital. It's always the lowest energy orbital in that state. It's spherical. Once you get above n equals 1, then they all have 3 p orbitals, and that's from that m sub l number. And so these are referred to as px, py, and pz. They're not spherical, they have 2 lobes, and they have a node at the nucleus. So this is for 2p. So this is the fuzzy probability kind of picture, and this is looking at it more as a solid. So you could say, I think it's like 90% chance that the electron would be within that area. It does not mean that the electron is zinging around on the surface of this balloon. It doesn't mean that it's trapped in there. Just drawing those dot pictures is super tedious, and so we don't. This is where I think we can better envision the electron as being a standing wave. So, oops, didn't do that very well. So doesn't that look a little bit like the standing wave? Come back here, come in, on the string. So this p orbital, see, the electron is a wave. And the electron is, as a wave, it's occupying the whole space. But if we pin it down by taking a picture of it or identifying it in some way, it can only be at a given point. So sometimes students will think about, well, the electron's just like zinging around in there. It's really unpredictable. Like a moth around a flame. It's just flitting around. That's not true. It really is occupying this whole space. One electron is occupying this side and this side, even though it can't go through the middle. But a standing wave can have height on this side and that side, even though the middle's not moving. So there's one along the x-axis, one along the y-axis, and one along the z-axis. These are going to have nodes inside them as they go to higher levels, but we don't need to remember that. Any questions yet?
Yes.
Mm-hmm.
So the size and the number of nodes, how do I say this? Okay, so like say for s orbitals,
Mm-hmm.
as s orbital increases, does the size and nodes increase as well?
Yeah. So here we see on the second level, this s orbital is bigger than it was on the first, and it has a node. So it has this area here where there's no electron density.
It's bigger than the first one. Okay.
And then 3 is bigger, and it's got an extra node. So as you go up the levels, they add a node. Any other questions? Yeah.
So are these orbits depicting every electron in a atom, or is it one?
So each of these orbitals can have 2 electrons in it. So in this 1s orbital, there could be no electrons, or 1 electron, or 2 electrons.
So if an atom has more than that, is it just a combination of a bunch of orbitals?
Yeah. Yeah. So here with the p orbitals, each of these could have up to 2 electrons in it, so there could be a total of 6 electrons in this sublevel.
And they could all happen at the same time?
Yeah, and they're all going to be, these are perpendicular to each other, and so they're like standing waves jiggling around. Yeah.
And then why are these, not the shape, like why are they like similarly different? Like that one is on the axle, that one
So
is
they're-
next to each other?
Yeah, they're perpendicular to each other. So one is this way, and this is trying to show straight in and out, and one is
But
up and
it does
down.
the same shape?
They each
just
have
at
the
a
same
different
shape. This
angle?
just looks a little different because of the perspective.
Okay.
Yeah. So the d orbitals, jumping. Yeah, there's information about the d orbitals. This is what they look like. Like, well, okay. So these 4 kind of look like a double p orbital, right? It's got 4 lobes instead of 2. Well, what's this guy? It's a p orbital that doesn't know how to swim, so he's just got a ring on him. And then there's the f orbitals. Look at those guys. We're getting into some serious balloon art now, right? You may have to draw an s orbital or a p orbital. I will never make you draw d or f orbitals because they are ridiculous. So those orbitals are found from mathematical wave functions that are solutions of the Schrodinger equation. Wave functions can have positive or negative values. We say they can have a phase. They can be in positive phase or negative phase. And when two orbitals interact, they may be in phase or out of phase, and so they can, that becomes important in bonding. So this is illustrating the phase of an s orbital and a p orbital. So the p orbital is a little easier for me to understand because this looks a lot like a standing wave, right? So one of the lobes has a positive phase and the other has a negative phase. And so the p orbital of one atom can overlap with the p orbital of another atom, and depending on the phase, they might have constructive interference or destructive interference. Yes?
Can you, in this context, could you explain a phase, like a position?
Yeah, so if we're thinking about a wave on a string, the phase is whether that part is above the center line or below, right? And so you could say, well, isn't that flipping back and forth? Well, yeah, it is. So our analogies get kind of weak here.
But one's always positive, one's always negative.
Yeah, one lobe is positive and one's negative. And we'll talk a lot more about that later. They just want to kind of introduce that here. So we've got all of these crazy, and this kind of gets to your question, all of these crazy balloon art things, then why do we represent atoms as being spheres? Yeah, because when, it's just like this, when they can all be in and through each other, because what are they? They're waves or tiny particles, it's just really, you don't want to think about it too hard. But if you think about combining all of those different orbitals, you're going to get something that's roughly spherical, right? So. Mm-hmm.
He said that he described it like clouds almost, like clouds that kind of
Yeah.
overlap.
Yeah, you can think of them as being like clouds, because there's not solid objects, because those could not go into each other. They can go through each other and be in the same space. And yes, that's very hard to understand. Yeah.
So this is this still according to Bohr's model? Just
No. No.
Okay, this is past that.
This is quantum mechanics. Bohr's model, yeah, you're like, well, if this is Bohr's model, then quantum mechanics is going to be way worse, and this is terrible, right? No, Bohr's model has the electrons going in nice circular orbits, like the planets around the sun. We're comfortable with that. But this is
So is
what
this
they're really doing.
what is this what we believe they look like currently, or is there
Yes,
also-
no, this is
Okay.
the current accepted model. Yeah. And, these wave functions and things cannot be solved exactly. And so there's all kinds of extremely hairy math involved in this. And thankfully, we don't have to do any of it. Any other questions?